Welcome back, students. Today we're going to continue working with complex numbers and their operations. The only operation that we haven't done yet, we already did add, subtract, and multiply. The only one we haven't done yet is division. So before we can get into how to divide with complex numbers, we need to talk about complex conjugates. So in the last video, I started to get into complex conjugates. What it means is you have basically the exact same complex number. The only difference is the fact that the sign separating the real number from the imaginary number has changed from either a negative to a positive or from a positive to a negative. But what's really cool about complex conjugates is the fact that if you were to multiply them together, their product is a real number. So here, I don't actually have numbers substituted in. If I were to replace A with a number, I'd have to replace it in both places. And if I were to replace B with a number, I'd have to place it in both of these. But in general, if I were to use these variables to represent these, when I were to multiply, I'm going to multiply A times A, which would give me A squared. I'd multiply A times negative BI, which would give me a negative ABI. And then I'd multiply BI times A, which would give me positive. Put those in alphabetical order, A, B, and then I always goes at the end. And then if I take positive BI times negative BI, that's going to give me negative B squared I squared. Okay, I can do a few things here. Minus ABI plus ABI, those are like terms. They are almost identical terms, except this is a minus, this is a plus. They cancel each other out. So this leaves us with A squared. And then minus, we have B squared. But I squared, by definition, remember that we know by definition, I is the same thing as the square root of negative 1. So that means that I squared is equal to negative 1. Technically, if we were to write I to the third, this would be negative 1 times I, which is negative I. And I to the fourth is negative 1 times negative 1, which is positive 1. Okay, make sure you have those memorized. All right, so I squared, I would never leave it as I squared. I always simplify as much as possible, and I squared is negative 1. So this is going to give me A squared, and then negative B squared times negative 1 is plus B squared. Every single time. It doesn't matter what A is, it doesn't matter what B is. If I multiply two complex conjugates together, it's going to eliminate the imaginary part every single time, and what I'll be left with is A squared plus B squared. So let's get into identifying conjugates of a complex number before we actually start using it. So if we have the complex number 3 minus I, 3 is the real part, I is the imaginary part, and we're subtracting. So the conjugate of that, the complex conjugate, is going to be 3 plus I. Only difference is the sign in between the imaginary and in the real. 5 plus I, that'd be 5 minus I. 9 minus 2I, that's going to be 9 plus 2I. Negative 4 plus 3i, it's the sign in between. So the negative 4 stays, but instead of having a plus 3i, we're going to subtract 3i. And if we have negative 7i, well, that's not a complex number. Right now, that's just an imaginary number. If we were to write it as a complex number, we could write this as 0 minus 7i. So changing the sign in between would give us 0 plus 7i, but we don't need this 0. It's just positive 7i. So if you have a pure imaginary number, all you'll do is change the sign. If it's negative, it becomes positive, positive becomes negative. But if you have the complex number, which means that you have the real component and the imaginary part, you're changing the sign in between. The reason why we need these is because we need to rationalize our denominator. Okay, in order to be able to divide, we are going to multiply by the conjugate of the denominator. So if we have 4 minus I divided by 6i, what we need to do is recognize what's the conjugate of 6i. That's a pure imaginary number, so its conjugate is just negative 6i. If I multiply by negative 6i in the denominator, I also need to multiply by negative 6i in the numerator. Because I'm allowed to multiply by the fraction of 1, doesn't change the value of the fraction, it just changed what it looks like. But if I only multiply by negative 6i in the denominator, that changes my fraction completely. So I'm going to multiply by the conjugate on top and on bottom. So hopefully you're really good at foiling or the Punnett square or using double distribution. Whatever it is you call it, we need to multiply. So we're going to take 4 times negative 6i, which is going to give me negative 24i. Then we're going to take negative I times negative 6i, which is going to give me positive 6, and then I squared. Over 6i times negative 6i is negative 36i squared. But remember, I squared is the same thing as negative 1. All right, so this right here is really negative 1. So I'm going to have negative 24i plus 6 times negative 1 over negative 36 times negative 1, which, switching my order around, is going to give me negative 6, a real number, minus 24i over negative 36 times negative 1 is going to give me positive 36. Okay. Thought you might be finished, but you are wrong. We can simplify this. I've kind of run out of room, so I'm going to come up here. What I'm going to do is I'm going to separate my real component from my imaginary component. So this is going to give me negative 6 over 36 minus 24i over 36. And then simplify your fractions. So negative 6 over 36 is going to be negative 1 over 6 and minus the fraction 24 over 36. Both of those are divisible by 12, and that is going to give me 2 over 3. And then it has the I with it. So my final answer would be negative 1/6 minus 2/3 I. Next example, my denominator has 3 plus 2i, so I need to multiply by 3 minus 2i. I'll do so on top and bottom. So in my numerator, I'll distribute, and I'm going to get 15i and then minus 10i squared all over. I'll FOIL or use the Punnett square or double distribution in the denominator, but 3 times 3 gives me 9. 3 times negative 2i is going to give me negative 6i. 2i times 3 is positive 6i, and 2i times negative 2i is negative 4i squared. All right, so replacing my I squareds and combining like terms. In my numerator, my I squared right here gets replaced with negative 1. So this is the same thing as having negative 1. So negative 10 times negative 1 is positive 10 plus 15i over, and my denominator, my negative 6i plus 6i cancel out as complex conjugates. If you multiply them, they will always cancel out. And then I squared is the same thing as negative 1. So what we had was 9 minus 4 times negative 1. So negative 4 times negative 1 is positive 4. So 9 plus 4 is going to give me 13. I could try to simplify this, but when I break it apart into my real component, which is 10 over 13, plus my imaginary, which is 15 over 13i, none of my fractions simplify, so this is my final answer. Next example, again, I'm going to multiply by the complex conjugate of the denominator, so 2 plus I on top and bottom, and 3 times 2 is going to give me 6. 3 times I is going to give me positive 3i. Negative I times 2 is negative 2i, and negative times positive is negative. I times I is I squared. Over, I'll multiply this. 2 times 2 is 4. 2 times I is positive 2i, and then negative I times 2 is negative 2i, and then negative times positive is a negative, and I times I is I squared. Combining like terms and also replacing I squareds with negative 1s. So if you want to, instead of writing I squared, just go ahead and automatically write negative 1. Go for it. It'll save you a little bit of work. So this is going to give me 3i minus 2i is I, and then 6 minus negative 1 is going to give me 6 minus negative 1 is going to be 6 plus 1, which is going to give me a positive 7. And I'll put the real number before I'll put the imaginary. So this is 7 plus I, and in the denominator, complex conjugates, the middle parts always cancel out. So I'm left with 4 minus negative 1. So 4 plus 1 is 5. So if I split this up, this gives me 7 over 5 plus 1 over 5, or just I over 5, however you want to write it. None of those fractions can simplify, so there would be my final answer. All right, the next one is much of the same. If you want to see this one worked out, go to the notes. But here I'm just multiplying and I'm multiplying, or no, I'm not multiplying, I'm dividing, which means I multiply it by the complex conjugate. So if you want to see this worked out, you can. I'm going to move on to the next topics. All right, so factoring. Okay, before we only had 3 factoring formulas for binomials. We had a squared minus b squared. We had a to the third plus b to the third. We had a to the third minus b to the third. This one didn't exist, where we had a squared plus b squared. You don't have to, but it can work out now that we know the imaginary number. This, where we get a squared plus b squared, is just what happens when we take complex conjugates and multiply them together. So for example, if I tried to factor 5x squared plus 20, first thing is it's in order. There is a GCF of 5. And then what I'm left with is x squared plus 4. In the past, we would have just left it like this. But we can take it further now because we have x squared plus 4. So we can think of that as x squared and 2 squared. So plugging that into the formula, that would give us x plus 2i times x minus 2i. Final answer. So the next one, we have 3x to the third plus 27x. Your first instinct would probably be to use a cubic formula, but always check order and GCF. So it's in order, and there is a GCF. The GCF is 3x. So what we're left with is x to the second plus 9. Okay, so that x to the second plus 9, we can use the above formula and write this as x plus 3i and then x minus 3i. The reason why we need to make sure to include the i's in there is because 3 times negative 3 is negative 9. We want positive 9. We'll get that by multiplying I times I, which is negative 1. So you can either choose to use those formulas from up above to solve these quadratic equations, or you can just use by definition of imaginary numbers. But we can solve quadratic equations using complex numbers. So for this one, we'd add 9 to both sides, and we get negative 3x squared equals 9. Divide both sides by negative 3, we get x squared is equal to negative 3. Square rooting both sides, we need to make sure to take the positive and negative values, but we get the positive and negative square root of negative 3. Type that into a calculator, it's undefined or it's an error, but we know better, and this is going to be, whoops, got ahead of myself, sorry. This is going to be the square root of negative 1 times the square root of 3, which by definition, we know this will be I times the square root of 3. So over here, we'll have 3/4 x squared is equal to negative 12. Then divide both sides by 3/4, or multiply both sides by 4/3, or split it apart and take 3x squared multiplied by 4 first to give us negative 48. And then divide both sides by 3, we get x squared equals negative 16. Square root both sides, we get x is equal to positive or negative the square root of negative 16. So x is equal to positive or negative square root of negative 1 times the square root of positive 16. So x is equal to positive or negative. Square root of negative 1 is I, and the square root of 16 is 4. So final answer is x equals positive or negative 4i.